Hello and welcome. My name is Haibin Zhao from Techco Research Group at Karlsruhe Institute of Technology in Germany. In this talk, I will show you a learnable sparse wavelet layer which can improve the performance of human activity recognition models. This is joint work with my colleague Yeshu Zhou, Till Riedel, Michael Hilfenburg, and Michael Beigel. Human activity recognition refers to classify human activities from sensor data such as IMU data through a machine learning model. Currently, there are multiple state-of-the-art human activity recognition models such as DeepConv LSTM consisting of convolution and LSTM primitives, the SAHAR model consisting of convolution and attention primitives, and MCNN model consisting of only convolution operations. As we can see, there are always convolutional operations in these machine learning models, and these convolutional kernels usually function as the feature extractor in the model. However, there are a few drawbacks with the convolutional kernels. Firstly, the values in the kernels are usually randomly initialized and optimized only by the loss function on the training data. This data-driven optimization method discourages the value in convolutional kernels from exploring the whole search space. Moreover, since the training of neural networks is usually an unconstrained optimization, the necessary properties of signal filtering such as bioorthogonality cannot be held. And finally, all these drawbacks drive the trained neural network and the trained convolutional kernel to overfitting the training data. To mitigate these shortcomings, we apply the wavelets as the feature extractor, which is usually designed by the expert knowledge instead of data-driven designing. Moreover, plenty of wavelets expressing fruitful underlying information and the critical properties of signal filtering such as bioorthogonality and energy conservation can be held. We therefore believe that by combining the wavelets with HAR models, the performance can be improved. In this regard, we proposed the learnable sparse wavelet layer, and this figure shows an overview of the proposed layer. By filtering the original signal through wavelets, we obtain multiple signals. These signals are then multiplied by the learnable informative factors to reflect the informativeness of each wavelet. The processed signal is then put into the HAR model for activity recognition. To further reduce the computational cost of the wavelet layer, we introduced the filter pruning. In the next slides, I will introduce the details of the learnable sparse wavelet layer. To prepare the mother wavelets, we select all the discrete wavelets provided by the PyWavelet package and resampling them to the same length as the sliding window in the dataset. This is an example of HAR wavelet. Subsequently, we remove the wavelets with high similarity based on the correlation. Because they are similar or even identical wavelets. For example, the HAR wavelet is exactly the same as the DB1 wavelet. After the removal, we introduce the temporal scaling factor. To achieve this, we downsample the original wavelets and zero padding them to the original length, as shown in this figure. Lastly, we introduce the informative factor to indicate the informativeness of each wavelet. This is a learnable parameter which will be optimized together with the HAR machine learning model. To further decrease the computational cost, we introduce the filter pruning. That means we add the L1 norm of the informative factor as the penalty term into the objective function so that more informative factor will be driven towards zero. After training, we will remove the low informative factors as well as their corresponding wavelets. After the removal, we will fine-tune the model to mitigate the influence of pruning. The bottom part of this figure shows the layer after pruning, and we can see fewer wavelets remain after the pruning, and fewer data will be put into the machine learning model, which can also decrease the computational cost of the HAR model. To test the effectiveness of the proposed learnable sparse wavelet layer, we conduct experiment with 6 benchmark datasets, namely the Opportunity, Skoda, PalmUp2, DSADS, DAFnet, and Wisdom. Regarding the HAR models, we preponed our layer to 3 state-of-art models, namely DeepConv LSTM, SAHAR, and MCNN. To modify the size of the model, we employ the model size scaling factor equaling to 1, 0.75, 0.5, and 0.25. We run the baseline models. We also run the baseline models with the learnable sparse wavelet layer, and we also run the baseline model with only learnable wavelet layer without pruning. As evaluation metric, we choose the macro F1 score to show the performance of the models and the number of floating point operations to show the computational cost of the models. This is a comparison of the baseline model DeepConv LSTM with and without learnable sparse wavelet layer. The dashed line is for the baseline and the valid line is for the model with the learnable sparse wavelet layer. We can see that the layer improves the overall performance of the HAR model, and moreover, on datasets such as Opportunity, Skoda, DSADS, and Wisdom, the performance of baseline models reduced with decreasing model size. That means the baseline models don't have enough parameter to deal with the tasks. In this case, the expressiveness of the wavelet can compensate this weakness and thus improve the performance. And moreover, the smaller the model size is, then significant the improvement will be. On datasets such as DAFnet, the performance decreases with increasing model size. We speculate that the model overfits. In this case, the wavelets do not overfit, and thus improves the performance of model with larger size. This is the result with other 2 baseline models, namely SAHAR and MCNN, which are indicated by purple and blue color. We can also find the similar conclusion from these baseline models. To test the effectiveness of the filter pruning, we compared the wavelet with and without filter pruning. The dot line is for the learnable wavelet without pruning, and the valid line is for the layer with pruning. We can see from the figure that the pruning do not significantly reduce the performance of the layer, but it saves large amount of computational cost. This can be seen from the bar where the dark part is the advantage of the floating point operation provided by the filter pruning. We also do the same experiment with the other baseline HAR models, and we can also get the similar conclusion from them. To conclude the experiment, we can see that the learnable sparse wavelet layer improves the overall performance of the HAR models. It can not only mitigate the overfitting of HAR models with large size, but also compensates the feature extraction of HAR models with small size. It is also worth to note that, as a side effect, the improvement is more significant when the model size is smaller, and this property makes the proposed layer suitable for portable devices and wearable devices. Thank you for your attention.